Hi there everyone. So as Massimo said, I am looking at using gamification with crowdsourcing methods to annotate data, which is then goes on to be used in the supervised learning task for training supervised machine learning models. So a little bit of a quick background. The motivation for this method generally is that experts are very expensive, and using experts doesn't really scale. So we can, if we get lots of linguists and use them to annotate data, that will take a really long time. So the general crowdsourcing idea is, what if we could take 5 non-experts and make them equivalent to 1 expert? Different approaches have been used for this. The most kind of obvious approach is micro-work crowdsourcing, which I'm sure a lot of you are probably familiar with, and that's that we use something like Amazon Mechanical Turk, and we pay workers a very small amount of money. There's some lots of positives to this. Work starts right away. There's also some negatives. There's not really training opportunities when using crowdsourcing. When you recruit a worker in, they kind of expect to be paid right away. If you're going to train them, you've kind of got to pay to train them as well, and they can leave the task at any time. So this is sometimes combined with gamification. Another problem is that there's quite often some spam in there, so you have to do some work to eliminate that, because using monetary rewards or generally any kind of extrinsic motivation can lead to rushed or prompt answers where people want to reach the goal as quickly as possible. So it can be expensive for large tasks, and it doesn't always scale particularly well. Another approach is citizen science. So you can see you have fold it in the background here. The way citizen science really works, the core motivation is that people are really interested in the scientific task. The problem with that is that not all scientific tasks give the end user an immediate gratification. There's lots of scientific tasks that are done in small bits, as opposed to some tasks like Fold It, where you could potentially tackle a single task in isolation to a great scientific reward. And then we have games of purpose. Games of purpose are a game where people play a game, and as a byproduct of playing that game, they're producing some sort of annotation or performing some kind of task. So there's some pros to this. After the initial cost of the game development, there's hopefully then very little cost thereon. However, there's also some cons in that this presents some really big game design challenges. But if you can make it work to effect, then you can scale to really large user bases of games played, and games are very popular these days. There's also some really good training opportunities as well. Games are great at training people. People can really learn a lot from playing games. Games have nearly always had tutorials and various other learning mechanics. So focusing on games with purpose, that's kind of the way we went with our work, because we're looking at some quite complex tasks, and we kind of need to make use of those training opportunities when we're working with annotators, non-experts, to annotate complex linguistic entities. So this example here is the ESP game. So this is image labeling. And what happens here is 2 players come along, they provide images for this, they can't see each other's labels unless they agree. When they agree, they get points. So effectively what this is doing is gathering labels for images through a game. So onto the language. Here we've got an example of an NLP pipeline. So for those of you not familiar with natural language processing, classical approach is to handle natural language processing in a series of steps. Obviously, there's some other modern approaches now, like end-to-end neural network systems, but the classical approach is handling in a series of steps. And we kind of do annotation in the same way, really. So very first of all, there'll be tokenization, splitting these items into separate elements, which poses some complications. We don't really use crowdsourcing for that much anymore. Parts of speech tags, which you can see identified here. So these are things like the nouns, verbs, pronouns, see in blue there. And then the next step we go on to is mention detection, where we find sort of what would be the noun phrases in the sentence. As you can see, those identified here by the curly braces. And then we quite often link those, which we call coreference resolution, where we link the noun phrases together. So we can see that he here refers to a wolf, and this is the sole reference, or this because this calls move, for example, one animal here killed. So, how do we do this with a game with a purpose? So this actually, the reason I described the ESP game in such detail is Tartac is inspired by the ESP game. So if we take the ESP game model quite literally and we translate that directly into natural language, we get, this is a web-based 2-player game, and it's ESP-like but for mention detection. So points are awarded again based on agreement with the opponent. And another crucial element to this, though, is that the opponent can be a pipeline. In fact, we work a lot with correcting a pipeline. This is a pattern that's used quite heavily in annotation tools. So for an annotation tool, they'll often prime the system using some sort of automated pipeline to reduce the workload of the annotator, or better inform their judgments. So there's a very quick video there of what they see when they enter Tartac. And we get this opportunity to give them a tutorial. So when we put this on crowdsourcing tasks, it's mandatory that they complete the tutorial. It's not something that would easily fit into a lot of crowdsourcing interfaces. So here we inform our users by actually using the step ahead coreference resolution to let them know about the items that we want them to mark. And here's some general gameplay. So the users go through and they use this quite simplified interface. I don't know if anyone's used annotation tools before, or even annotation tools via crowdsourcing, but normally there's a few challenges. There's a bit of a learning curve. Part of what we do is sort of HCI methods to try and simplify the process of identifying these things and make them really available to non-expert annotators. As I said before, the second player can be one of, first of all, that automated pipeline that we mentioned. But the other thing we do then is we use replays of previous players' games. But also, so we've got this kind of continuously improving annotation base, is we take a silver standard, what we call a silver standard or aggregation of all the prior player responses. There's two methods here that we'll experiment with, one of which is majority voting. Those of you who are familiar with majority voting is simply counting each annotation as a vote. The problem is that it makes the assumption that all the users are equally competent. So instead we've got a second approach, probabilistic aggregation, which is based on Davenant scheme. There's a few complications because we're working with heavily nested markables. But this then can effectively model the competency of our annotators based on their inter-annotator agreement. To achieve this, we need some way of clustering those mentions. I don't know if you remember the mentions that I showed you before, but we need some form of being able to say when they're related. So when I should consider two things as voting against each other in competition. To do that, we take a dependency pass and we have an algorithm that kind of loosely matches these trees, because we've got to work on the assumption that the dependency parser could potentially be wrong. If the dependency parser was always right, then we could probably stop there, because most of the time it would be identifying the correct markables. So then what we do is we take some pipelines at the start and we aggregate our user annotations on top of those pipelines. And we have a graph here showing that. So we've got the first two pipelines over here, which I believe was the popular Stanford core pipeline, and a dependency pass. And then we have majority voting, probabilistic aggregation applied to these. You can see once we get up to 5 annotations, including those pipelines, we actually exceed the state-of-the-art dependency parser that we used here, which compared very favourably to other pipelines. So this was a work published recently in ACL, for those of you who'd like to find out a bit more detail about that. Another issue that we have then is when we're thinking about all those different levels of skill of our annotators, is how we can best use their time in terms of resource allocation, but also how we can best keep them engaged. So we want to make sure that we're matching skilled users with skilled tasks. and we also want to make sure they're kind of having fun as well. So what we do is we introduce this notion of progression. And I don't know if any of you have seen before, this is Csikszentmihalyi's flow, and this is a modified diagram for games, and the idea is that you keep them in this state of somewhere between boredom and anxiety, in this zone that they kind of enjoy operating in, so they're in that state of flow. So yeah, as I say, how we achieve this is progression. So we're using our aggregation model again. And then once a player performs above the interquartile range against that silver standard produced by our aggregation model 3 times, they then continue on to the next level. So this is quite effective in resisting the changes of the documents. So what we did here is we took a set of documents that had been hand annotated with, but from a corpora that had been annotated with difficulty levels. Not particularly granular difficulty levels, but broadly into 5 levels of difficulty. And you can see here we've got a random group shown in blue and the progression group. And as the task increases with difficulty, our progression group is far more resistant to the changing difficulty of the annotation task that we provide them. So now I'm going to get onto some HCI stuff, because tile attack is great. Tile attack worked really well for us with crowdsourcing, but we come to the problem of how do you get people to, in true game with a purpose form, how do you get people to come and play a game without any financial incentive whatsoever, and also stay there for a long period of time and continue to play? So the obvious answer probably looks something like this. You just take an existing computer game off the shelf and you have your players start shooting word labels. I mean, who doesn't love playing Call of Duty over, right? It's a hugely popular title. The problem we run into straight away here, and this is, I'm getting into some kind of game design stuff, but is orthogonal game mechanics. And that's the idea that we don't really want a game mechanic to negatively impact our annotation tasks. So if someone's bad at shooting but good at labelling, we don't want to be getting bad labels from them. That ruled out a lot of existing games. And it also informed this decision that we needed labelling to be part of the core mechanic of games that we created. A similar problem with ludic efficiency, where we wanted, we didn't want games to, I don't know if anyone's played things like Mortal Kombat here, we have to enter a series of key presses. We didn't want that to really inhibit our user's ability to be able to provide judgments. Another problem is cost. If we're going to compete against modern games, many modern games have costs that run into the millions. But we are always competing against other crowdsourcing methods. So if, for example, we're going to compete against Amazon Mechanical Turk, $265 million would go a really long way. So this rules out many conventional games as well. We need infinite gameplay. We need players to be able to keep playing and playing and playing, because we have an infinite number of potentially, or we should see it at least as an infinite number of items that we might want to be annotated. We cannot be creating narrative, story, gameplay with a constraint of, say, for example, 8 hours, like a typical game might, because we'd probably, the costs involved in doing so would probably exceed the costs of the annotation we want. And we want to appeal to a broadest audience as possible. So the solution, we come to all these ideas, a simplified solution that we could quickly adapt was one of using clicker games, which possess all these qualities. Now, clicker games are kind of interesting because they were originally created as a satirical work by someone, really parodying real games. But there's a lot of really interesting game design ideas that have gone on here. Firstly, starting with, for example, Zynga and the creation of real games, and then Ian Bogost, who went on to create clicker games. And each time distilling down a set of mechanics into kind of a very fine form. So we then took this clicker game loop and adapted this, and we changed out the action bit. So at the centre of our game mechanics, then we had annotation for our action. We changed the wait part of the loop, and I'll show you more detail on that when I show you the video of the game shortly. But so that ingredients become cakes, become money. But basically, we design this part of the loop to find more labels. And then we reward the player by receiving currency, and they can then purchase upgrades from a shop. So one of the things we had to be careful of is how we use different mechanics, because there's a lot of sort of psychology and behavioural economics and design things that go into the production of these kind of games, although they seem quite simple from the outset. So we had to be careful not to disturb that when penalising users for incorrect responses, which is, yeah, so the two tasks had to be sort of fit together. But as I said before, this does seem to fit a lot of the problems that we described. In that we get rid of the orthogonal mechanics. We have a high ludic efficiency where we can present a tool in a way wrapped with a game wrapped around it. We have very low cost, and we have an infinite gameplay. So here's how this looks. This is the game word clicker we created to test this idea. And the idea is that here's sort of the annotation tool. In a sense, people pick ingredients, which are the word classes, and then click on a token to provide a label. And then we have animations to show the transition of ingredients into jars, and from jars into the cake. The more ingredient categories they've labelled, the more value they get from the cake. And they can purchase the upgrades over here in the shop. So yeah, there's a few kind of behavioural psychology ideas and the economics and psychology ideas that went into this, but this seems to tick a lot of the boxes for resolving those game design issues which we've struggled with before. So we deployed this on 3 indie games websites, and the idea here was that we felt that if we could finally truly consider one of these games to purpose as being a game, it should be able to perform alongside other games with a discerning audience of game players. Quite often in the past, such experiments have been carried out with undergraduate students or groups of people that are interested in NLP, but we really felt this should work with game players. And we had some really quite positive results from this concept. So the average session length was 27 minutes, which compares very favourably to previous games for the purpose. We had a lifetime judgments of 45.85. So for the lifetime of a session, a player would provide 45 judgments. That doesn't sound amazing, but one thing I should point out is that with all these approaches, whether it's be it citizen science, games the purpose, whatever approach you take, there is a power law distribution curve. That is the majority of the people provide the minority of the the minority of the people provide the majority of the contribution. So you have a top 5 players doing a massive amount of work, and then a very long tail. The other thing is that we have this has not been subject to any filtering or sampling, so it's quite low accuracy. But our players are learning over time. So there's 2 things we wanted to do with these work. And I spoke briefly about progression earlier and how I integrated progression into our crowdsourcing in the absence of a gold standard. But the other facet to this is that we enable progression between games. So having a user having learnt about labelling part of speech tags can then go on to label mentions. So there's a kind of a learning curve that goes on actually throughout the games. Invite any questions? Yes.